So yeah, today I guess won't be a typical research meeting because the plan is to talk about the research roadmap and kind of what's up ahead in the next months instead of an actual research topic. And Niels and I have been talking through this for the past weeks and also met with Jeff in December and kind of revised the roadmap a bit after that meeting. And now we thought it's a good time to share with everyone and kind of get everyone's feedback, and then we can finalize it. And I just have like a general first slide, which I hope will put everything a bit into context. And then Niels will go over the research roadmap in more detail. And I usually don't ask this, but maybe you can hold your questions until after Niels goes through his part, just because I don't want everything to stop on the first slide and then we try to discuss everything that Niels is going to talk about in the next slides.
That question addressed to me.
I'm not going to name any names.
Okay. I already broke it. I asked a question.
I mean, obviously, if you won't be able to follow without asking your question, feel free to ask a question, but I'm going to pull up the overview slide again after Niels' part, and then we can talk about everything in the big picture. Just want to make sure like we get the whole overview out first, and then we can talk about all the details. Hang on. Are you seeing my screen already?
Yes.
Yep.
Okay, awesome. Okay, so yeah, basically I thought about what's our high level goal, and this is a rough one I came up with. We can refine it together more, but basically we want to get our approach widely adopted, and I kind of divide it into three pillars. One is to achieve that, we need to make our implementation easy to use and to extend to reach a wide range of people who want to use this. We also want to actually have our implementation do useful things, so people actually want to use it. And for this, we need to implement everything that we figured out over the past years, all the research progress. And then there are also several larger open theoretical questions, and we need to make progress on those fundamental research questions as well, like object behaviors and manipulating the world are two big ones. And I guess they kind of build on each other. So first we try to make fundamental research progress, look at the neuroscience, try to figure out how the brain does things, then go into the implementation stage, actually implement it in Monty, test these ideas, see how well they work, if we forgot about anything, and then make it easier to use and try to get the community involved, try to get people to build applications based on that. And this is the very new aspect that we just now started, and we'll figure out a lot about in the next month, I'm sure. So just to go into a bit more detail of what these three entail. So making it easy to use and extend and getting it adopted and reaching a lot of people. One part of that is to document and educate people about the approach. Another one is to foster a community around it, find researchers who actually want to use this, who maybe want to extend it, who want to work with this, find people with applications, encourage people to test our approach. And then another part is to actually make the code easier to use and extend, and that involves some code refactors. And two bigger things on the roadmap there. And I'm not going to, in this presentation, we're not going to go a lot into this part of it because this is more focused on the research roadmap, but I have one slide that goes into more detail of the yellow part at the very end if we have time, but just on a high level note. Yeah, I won't go into too much detail on this part. So then on implementing research progress, Niels and I basically put down two bigger objectives. One is better unsupervised learning, which is required for the next one, which is actually testing our hierarchy implementation and seeing how well we can model compositional objects. So first, we need to be able to remove this assumption that we show one object per episode, and then system gets told when the next object is being shown, when the next episode starts, and that we give it labels. And there are several things that we have under this approach. And then once we can do this, once we can have compositional objects and move from one part of the object to another, and the system can deal with this, then we can actually test how well we can model compositional objects and how we can utilize the hierarchy that we implemented. And then on the research side, one of the big topics is going to be object behaviors, and we've been talking about that a lot in the past research meetings, since this seems to be an important prerequisite for implementing policies to manipulate the world, which is ultimately what we want the system to be able to do. Like being able to manipulate the world is like what the system will be used for in the future. And then something that will also probably play into this is thinking more about compositional policies and how we can hierarchically decompose policies. And then again, once we make enough progress on these on the theoretical side, they will end up on the middle column and actually be implemented and tested. There are several other theoretical questions that might come up in the next months, but that are not the main topics. One might be scale, object deformations, or dealing with abstract space, but just putting this on there since they might relate to some of these. And then in these research milestones, Niels and I were talking through this again and kind of divide both of them into two subparts, policies and learning module computations. And Niels will go into more detail of what these will entail. And then on the code refactor, we have this plan to refactor a data loader and dataset. Tristan already got started on some first refactors for this and has planned out the follow-up refactors. And after this is done, we can make the motor policies more modular, basically having motor modules. And this will be a prerequisite for part of this research milestone, which is why we have this focus here, so that we can make these code refactors that then support the research and implementing the research ideas. And then I just kind of marked the ones that are next up or in progress in green. So here we have the refactors. We have unsupervised learning as the big next topic, and then object behaviors as a big research topic. And I'm not sure if this view is useful, but I just kind of overlaid who will roughly work on which part, but obviously there will be overlaps. And so this is the next 3 months roughly, looking at unsupervised learning, thinking about object behaviors a lot from the research side. And then in the next 6 months, hopefully we can transition towards compositional objects, hierarchy, and starting to think more about policies as well, compositional policies and actually manipulating the world. All right, then I'm gonna... Oh, and the last thing is one thing we did to kind of encourage people, like especially the research team, not only to work on implementing stuff, but also to make progress on the fundamental research questions, is this new What I Learned This Week Slack channel. And just wanted to highlight here again that this is a big part of the work as well. So really encouraging people to also like keep reading, keep thinking about these fundamental research questions, and then we want to spend time on this as well. All right, we hand over to Niels.
Nice. Yeah, so I'm just carrying on where we've been left off, but I guess, yeah, as she said, I'm going to go into more detail about these things. But were there any kind of burning high-level questions just about, I guess, this overview? And yeah, you're welcome to ask me questions when I'm talking. It was just this first part that we thought it would be helpful to just kind of go through it in one go. Okay, cool. in that case, I'll continue. So this is just a slide from this last summer, June 2024, when we kind of set out what we felt were like the two main themes we wanted to focus on for the research, and those were hierarchy and actions. And I would say broadly, this hasn't changed. That's still kind of like the main things that we're kind of introducing and wanting to be working on. But what we kind of realized when we were kind of putting together these more kind of short-term goals was that so actions was always going to follow kind of hierarchy to a large degree. But before we could even really get to kind of hierarchy in an interesting way, we needed to improve unsupervised learning, which is why, we think this would be kind of the thing to focus on next. And then that naturally leads into compositional objects, where then the hierarchy kind of starts kind of manifesting. And this is a lot of text. I'm not just going to kind of read through this, but this just gives an overview of some of the kind of concrete things that we're planning on looking at in order to address unsupervised learning and compositional objects. But I think the kind of one thing to highlight is we already have a lot of things about Monty that make it really well suited for unsupervised learning. And we've already kind of implemented some of the groundwork for compositional objects. So when I'm talking through these kind of concrete ideas, it might seem like kind of a relatively random arrangement of kind of tasks, but it's because kind of most of the problems are, I would argue, kind of filled in terms of what we need in order to do things like unsupervised learning. There's just kind of a few sections of the sort of puzzle where we just need to kind of fill in and improve performance, or kind of make sure we have certain properties, and then hopefully a lot of this should start to kind of fall into place. And for both unsupervised learning and compositional objects, you can kind of broadly break them down, the kind of different projects, into the kind of overarching one, which is developing kind of a data set and evaluations that we're going to kind of look at for that particular task. And then, so that's kind of essential. And then within that, in order to kind of essentially solve that task, be able to kind of do interesting things, the two main places that we want to make changes are either going to be at the kind of level of the sort of learning modules, representations and computations, or at the level of kind of policies, although some of those will be kind of model-based policies. And that's also the case for the compositional objects. But yeah, so then unless there's any questions on that, my plan was just to kind of go through each one of these, and not in a super level of detail, but just kind of give a flavor of what the kind of task is, and I guess why it's relevant to these problems. And yeah, I guess one thing to start thinking about, Scott and Jose, I know you've both kind of mentioned projects that that have come up that you thought sounded interesting and stuff like that. But yeah, it's worth just kind of thinking about what you find particularly interesting burning questions under the supervised learning in particular, in terms of like what next projects we can work on later this month. So in terms of kind of a data set and evaluations for the unsupervised learning setting, the kind of good news is we're not planning on kind of going back to the drawing board or anything. We are going to just kind of use YCP as we have done. But as Viviane was saying, we really want to remove the assumptions we have right now about kind of supervisory signals, and those are kind of implicit and explicit. So like we have things where, we show for one episode an object, and then we kind of reset the network, we reset the evidence values. So that's kind of more of an implicit signal that like, okay, you've just learned one object, now there's a new object. But we also have kind of more explicit, and then we have more explicit information often where we're learning where we pass the label to the system, and kind of tell it whether certain episodes are associated with the same object. And we also have things like we give these 14 very idealistic views of every object, which really helps us get good coverage of the object and make sure we've learned all parts of it and things like that. So it's a really good kind of initial setup to have to kind of check the performance of the system. But if we want to move towards more complex, more realistic kind of situations, including the kind of compositional models. Because as soon as we introduce compositional models, there's very few data sets where the kind of parent and child objects are actually explicit and labeled or anything like that. Like we can, potentially construct a data set like that, but generally speaking, as soon as you have multiple levels of representation, some of those are going to be kind of implicit, and in any kind of direct supervision like we're doing right now wouldn't be possible. So that's the kind of data set side. And then in terms of kind of computations in the learning module side, so we discussed a few possibilities about how we are basically going to get learning modules to be able to deal with the fact that they are kind of moving on to new objects, and they're moving off the object they were on, back onto it, that sort of thing. And basically kind of not just having this eternal memory of kind of going throughout all time. And we think kind of the simplest solution that should work well is basically to have the evidence values that we currently have that accumulate just decay more rapidly. So what this plot is showing is the kind of highest evidence score associated with a given object as a function of the episode. And this is an episode where there's multiple objects. So depending on where the sensory patch is, these colors at the bottom show what object is actually being visualized by the system. So this is kind of ground truth information. So at the start of the episode, the agent is on the potted meat can, this like blue line, and it gets lots of evidence for that. And then around step maybe 32, 33, it generally kind of moves over to the bowl, and then it stays on the bowl for a while. And as we would like, the evidence values drift down, because once it's on the bowl, it's no longer getting evidence consistent with that. But even after it's been on the bowl for something like 15, 20 steps, it still has a really high evidence value for the potted meat can because it had accumulated so much. And this accumulation is essentially unbounded and has very little, if any, decay at the moment. I mean, it's hyperparameter tunable, but we don't do generally any decay right now. But what we think is if we just make this memory much shorter, then in general, the system should handle the kind of fact that it can move onto a new object. And then it's just going to forget about whatever object it was on before and start building new evidence. But in order for this to work well, we generally want it to move fairly efficiently when it is on an object, because it doesn't have that much time to accumulate a lot of evidence. And so what we want is, as the system is starting to do now with the kind of hypothesis testing policy, quickly move to kind of interesting features and things like that. But a big theme of the other work under this kind of unsupervised learning is adding things that will basically get it to explore these kinds of interesting features more and kind of more quickly converge. And so one of those is bringing voting over into the kind of unsupervised setting. So as well as just kind of in the single episode setting, we have supervisory signals. We also have those in when we do multi-LM experiments, because at the moment, the LMs, the learning modules basically know that they're all seeing the same object, and they know to establish a connection based on that. But if, as soon as we're throwing away supervisory signals and, we don't know if there's multiple objects or kind of, a larger object and a sub-object visible at a given time, we need to actually naturally learn these associated connections. So I think this is a nice problem to work on, because it's a kind of deeper problem that we had ideas for how to solve and kind of need for the long-term kind of capabilities of Monty. But it should also help nicely in this kind of shorter term focus on unsupervised learning. Because you can imagine in this case, if you have a collection of 5 learning modules, each with their own sensory patch, and they all move on to an object, you're quickly going to get evidence for or against different objects, and you won't need to do this kind of piecemeal kind of memorization of everything you've seen before. Of course, we're still keeping in mind the idea that a single learning module can do essentially everything that we need to do, or most things. So it's not that the voting is here to enable something that a single learning module can't do, but it's just going to help it do that more. robustly. And then, so those are the kind of learning module computation changes we were thinking about. And then on the policy side, I said we want to kind of move around more efficiently. And so for the distant agent in particular, the one that kind of saccades across objects, it's not doing things like this right now. It's essentially just moving these tiny little increments like a random walk. If it does any larger movements, it's based on this hypothesis testing policy, but that tends to move it in space rather than it actually kind of looking at a different point. So we have some ideas for both kind of model-free and model-based signals that will really help us kind of move to the kind of most relevant parts of the object much more quickly. And again, this is something that'll be useful for unsupervised learning, but is just like a really useful thing to have more generally if people are going to actually use Monty in the long term. I think this will make a big difference. And kind of a subtly different one is a specific focus on an exploration policy. So at the moment, the exploration policies are kind of designed to try and be fairly exhaustive, but they're still kind of dumb in that they just kind of follow some pattern of moving. Like, you know, for example, with the distant agent, it does this kind of spiral scan to try and cover as much as possible. That works really well in the kind of supervised setting we have right now, where we make sure we show each object from 14 different angles. But assume we just give the object, and then in that one episode, or maybe 2 or 3 episodes, but each time the agent just gets it from a totally different angle. In those episodes, it needs to learn, you know, all about the object and really explore it. And so in order to do that in kind of an efficient, principled way, we think model-based exploration policies would be really useful. And, you know, we can think more about what those heuristics might be, but, you know, just a simple thing like this, where you've seen kind of part of this bowl, there's likely a variety of ways that we can kind of have this heuristic that, you know, all these kind of gaps or these kind of edges of surfaces and things like that are going to be things or potentially kind of points of symmetry where you would expect to see an object, but currently there is none. These might all be points that kind of the agent tends to think, oh, that might be an interesting area to move to and to move around on. And then lastly, again, it's a subtle distinction, but there's this kind of important ability to be able to switch between a learning and an inference-focused policy. So at the moment, we do this switching explicitly when we transition from the learning phase to, or the training phase to the inference phase. And again, we're able to do this explicitly because we know when that transition happens, because it's a supervised experiment. But when we move to kind of true unsupervised learning, we, you know, the system can, you know, detect when that transition happens, but we also then need to actually define kind of this switch to happen naturally. This is actually more of kind of an infrastructure change, so probably fits more into what Viviane was showing on like the left-hand side with the kind of yellow boxes on the infrastructure stuff. So the hope is that kind of once some of those things are changed, it should be a relatively simple change. It's not implementing a whole new policy. That's essentially what the top 2 points are. But it will still be like an important point to kind of getting unsupervised learning working well. That's everything on unsupervised learning. Any questions?
I'm sorry, I didn't want to stop everyone from asking questions. It feels very wrong now that I said that, because it's such a different atmosphere.
I have a question on the previous slide with the accumulation of the points that a hypothesis is getting. Where you had the graph.
This one?
Yeah, that one.
Yeah.
So as you saccade around and you move off the object and you sense something potentially new, like it goes from a mug to a banana, and now you're sensing banana. Like rather than start decreasing the score for that object, another possibility might be just create a whole new thing that you start scoring for, and then if you go back to the mug, then you can start adding points to that again. Like, so in the learning module, we'll have multiple hypotheses that you're keeping score for, or do I Have I misunderstood everything?
No, I think it's a fair point, and I guess there's two kind of things about that. So one is, yeah, we've also discussed that we might just kind of have a system so that the learning module thinks like, okay, I've moved off of this object. I was on it, but I've now moved off. So I'm going to basically just reset my evidence values and then start accumulating for whatever I'm on. We wanted to try first to see how it works with this kind of evidence decay. But that's another possibility. The, I guess, other thing is that, yes, definitely, that is also important, and that's where the hierarchy will come in. So we don't think it would be the lower level learning module that's keeping track of both objects. Like the lower level learning module would still forget about the potted meat can after it moves on off of it and it's on the banana. But assuming the potted meat can and the banana both exist in the world, and those are kind of both possible or like locations for those objects, as it moves off the potted meat can onto the banana, a higher level learning module, which is modeling something more like a scene, would then understand that, oh, okay, now I've moved onto this banana that it's receiving from the lower level learning module. And then when you move back to the potted meat can, that high level learning module could then reinstate the potted meat can representation in the low level one. So yeah, so once we're not doing kind of multi-object, like we're not doing like scene-like data sets now. That was one thing we kind of discussed with Jeff that we want to kind of wait with doing. But with the compositional objects, which are kind of multi-objects to a certain degree, that will definitely be yeah, important.
I guess the way that I was thinking to Will's question was that we don't. I guess one thing is that we could learn that we have moved off from potted meat can and went to banana, but then in an unsupervised setting where we don't have the labels, we don't know maybe that we have moved off. Like, is maybe it's possible that we're actually seeing a potted meat can fused with a banana and it's actually one object for whatever reason. So I don't think there's like a straightforward way to say like, okay, like I'm in a different potential object that I can start accumulating for. Maybe if we see this trend where it's like, okay, well, I'm continuously losing potted meat can, and after like some episodes, after we lost like 10 points, let's say, then we can say like, oh, have some kind of rule to say like, okay, let's just accumulate for a new one. But yeah, but like we have to assume in this case that like we don't know if we're actually going to a new object. If that helps.
Yeah, yeah, no, definitely. And I think one thing that comes into this as well, which we don't have a specific point on here, but I think will kind of be important, is just in terms of like with this kind of unsupervised learning, how you kind of forget things over time. So that you kind of might initially have built, like let's say the first time you encountered a compositional object where there was multiple things together, you learned that as one object because they were together. As you say, like you don't know when you're moving off of one object onto another. But over time, you might see, oh, okay, the logo was I saw that, in one instance at one time, and then in another associated with a different object at another time. So you'll start kind of forgetting the kind of all the information that was fused to the logo and developing that as its own kind of singular representation. Yeah, so I think that'll be really important. It's basically an unsupervised learning thing that we need to do for compositional objects. We don't necessarily need to do it for this most basic unsupervised learning, which is where we remove kind of one episode per object.
So
I guess we might need to a certain degree, I guess, in terms of like the episode transitions, but yeah.
So I don't have any questions about what you're all presenting. It's really great. I have a lot of ideas on how to implement this, but I don't think that's what we want to do right now. Is that correct? So I don't mind writing those up and posting them after this meeting. But
yeah, sounds good. Yeah, and then maybe yeah, I mean, I guess there's a chance we get time to discuss that at the end, and then otherwise could discuss those like next week or something.
I'd want to write them. I'm taking notes. I'd want to write them up just so that I don't forget them.
Okay, nice.
But I assume that's Vivian's comment early on was like questions if you don't understand, but maybe not try to solve all these problems right now. So
Yeah, I think we
I'm
should
just- I'm-
definitely talk about any additional ideas. I just wanted to make sure we get like the big picture and the roadmap into
Right.
everyone's head first, and then we can talk about the details afterwards. But yeah, I definitely didn't want to say this is not
Well,
up for discussion or something like
I've
that.
got 5 specific ideas already on how this, how we might go about this unsupervised learning. It's on top of what you already presented. So, but they could take an hour. So I think I'll just leave them for now and I'll write them up after we're done here. Because I'll
Nice.
probably have like
Yes.
some other ideas too. So, but it's all good. I have no question. I like the way you're organizing.
Nice. Yeah, no, that sounds great. Any other questions on the unsupervised learning stuff? Or comments?
It seems like some of this stuff kind of, especially this bowl picture,
Yeah.
ties into something that's been on the research roadmap for a while, which is using negative information. Like there's a difference between a point that hasn't been explored and a point that has explored, and you know that there's nothing there, kind of thing.
Yeah. Yeah,
Just
we
about-
talked a bit about whether to include that here. I guess the first point is, yeah, there's like the negative information that you might get where you have a model of an object, you move off, you don't see anything. And I think we felt that's most important for like kind of scene-like arrangements where you're moving through empty space a lot, because we're going to be trying to move on, start with like simpler compositional objects where it's kind of like everything's in one place. It's not as necessary, and so we might just kind of wait with that just for the sake of prioritization. Regarding
I
kind
think-
of, oh yeah, I was just
Uh,
going to quickly say, and then as like maybe a separate point is just, and I'm not saying this was what you were kind of suggesting, but one thing we don't want to do is store negative information. Like we don't want to like actually have to explicitly say, oh, there's nothing here, just because then it becomes like an unbounded like cost associated with that. But yeah, anyways.
Right.
Yeah, I think another big thing was that the idea we originally had was related to like the fact that we can detect when we're not on the object, like since we have an object floating in empty void. But once we move to more realistic scenarios, there will never be an empty void. So whenever you move off the object, you'll still sense something. We still want to be able to use this information eventually. Like if I predicted to see a certain feature, but then I saw something different, we still want to be able to use that. And we are using it to a certain degree, but I think we'll need to think a bit more about it, how we would use it if it's not this explicit off object signal.
Yeah.
That makes sense. Thank you.
Nice. Okay, and then the other kind of main theme then that will kind of follow up on the unsupervised objects, unsupervised learning then is the compositional objects. And again, this kind of starts with like making sure we have kind of a data set and evaluation pipeline that we can actually explore this in. And this will probably be something we revisit and isn't kind of finalized what the compositional data set would actually look like. But I guess the most recent thinking is that it would be something like this where we might have kind of a series of like 4 objects, say, and 4 different logos. And those logos can be associated with each one of those objects, as well as you can have the objects and the logos in isolation. And basically then we kind of learn in an unsupervised way on that data. And this kind of avoids some of the kind of awkwardness we had with the dinner table scene, which has some advantages in terms of like policy and stuff like that that we don't need to get into. But this basically is just a simpler in general compositional object, but also enables us to explore some interesting problems, which I guess are on the next slide, which is, I think this is a really nice example of a research idea that we have like a good idea of how to implement it and what we expect it to do, but we just haven't implemented it yet, which is kind of having these location-specific compositional representations where if you have something like the Numenta logo, which is bent at this angle, that you'd maybe use, two kind of learned associations to represent that, but that as the kind of deformation between the logo and the object and the mug becomes more extreme, you need kind of more neural hardware, or in this case, more associative connections to map that relation and kind of understand it. And yeah, I think it would be really interesting to finally test this idea, because this is something we've discussed for a while, and is very much kind of implementable, and is something we could explore with this kind of data set.
I just want to make the argument here that this location specific representations, I don't think is just for sometimes like the bent logo. I think it's all times. I mean, everything is represented.
Right.
Yeah, just want to make that clear.
Yeah, no, that's a good point. Yeah. I guess it'll become most like it'll make itself most apparent in this situation, but
it'll make itself more
Right.
apparent. That's correct. And because otherwise, like myself and Subutai and others, we've spent years assuming somehow you could represent the logo as a unit on the cup, and we just had to abandon that. So that's going to be true for all compositional objects. And then I think the harder part here is just how do we not have to learn every point, right? How do we, which is a general problem of the system, we need to extrapolate. So you really need to focus on, at this point there's a change, and then after that you don't have to remember everything.
Right.
But, yeah.
And so once we then have a data set, then they kind of, on the learning module computation side, the kind of main thing we need to add is the top-down connections, which again, I think we have a pretty clear idea of how these should work. As Jeff is saying, these are going to be location specific and in all instances. But it's a case of, obviously implementing the code and testing it and things like that. And then another thing that we've discussed that would be relevant here is this possibility of kind of re-anchoring hypotheses. So what that kind of means is, if you're familiar with SLAM, or even if not, if you think about path integration, as you move, you are integrating movement and you're getting sensory information that's kind of reinforcing where you think you are. But at the moment, we rely very heavily on that path integration. We kind of assume it's essentially noiseless and close to perfect. But what real robots have to do, in the grid cells and the entorhinal cortex, and probably us in this situation, is at certain times, if you get strong sensory information, that will kind of recalibrate where you think you are in that map. So for example, your doorway might be kind of a very prominent landmark in your living room. If you touch your doorway, you close your eyes and you walk in a circle, you'll maybe have a sense of where you are back now. But if you touch your doorway with your eyes closed, then you are very certain about where you are again. But anyways, this could operate both at the level of single learning modules and also in terms of hierarchy, in terms of like what the high level learning module is telling us where we should be and re-anchoring location. Yeah, so that's just something that be interesting to explore. But likely this will help just with noise, but also kind of distortions as we get into things like this bent logo, or kind of a logo kind of distorted by the side of a mug. And then lastly then are the kind of policies that then, again, these are quite general, but we think will be particularly helpful in the case of the compositional objects. And there's kind of two themes. One is kind of policies to sort of recognize an object before moving on to a new one. And then the other is that once you recognize an object, move quickly to a new object. So that you basically, when you look at the world, you kind of get a sense of what you're seeing, and then you move to the next interesting thing, rather than just randomly looking around, constantly being confused about what you are looking at. And so, yeah, this, again, just brings in things like saccades, where, you can imagine looking at this, or, and then kind of doing 2 or 3 movements on it, confirming what you think it is, and then, okay, what's the next interesting thing as you kind of move on. And all of this, as kind of Vivian's earlier slide show, kind of is eventually leading into things like object behavior. And, I thought it was just worth kind of revisiting. This was, the example that Scott suggested of kind of a lamp with a switch. And, this is a very simple compositional object, not dissimilar to a mug with a logo on it, but you can already imagine very complex behaviors and motor policies that we might want to try and learn. How can you maybe generalize from the understanding that, okay, this is a switch and this is a lamp, and then this is a lamp with a totally different morphology, but maybe you still understand that you're meant to look for this switch in order to turn it on, and at least the kind of
where'd you find that picture? That's an amazing complimentary picture. That's impressive. He got the switch and everything. Wow.
Right. Yeah, just Google, I guess. But
wow.
Yeah, so I guess it's just to say that hopefully the simplicity of the compositional data sets we're proposing doesn't give you the sense that, we're just kind of going into a narrow tunnel and this isn't going to be relevant for later things. Like, I think as Jeff often remarks, like a very simple task is often a useful way of kind of understanding a much more complex problem. Yeah, Vivian, do you want to?
Yeah, I mean, you can.
Or do you want me to just keep sharing?
Screen up, and we can just have that overview and talk about any comments or questions or suggestions.
Yeah, are you guys seeing the screen again? So I've
Yeah.
got two monitors, so I just want to make sure. Okay.
I was just thinking, I don't know who would be able to do this because I'm not friends with people in like computer vision labs, but it might be a possibility to put out there on a forum or something to say, hey, we are looking to work with new data sets. If you are a lab that, can scan these objects and do some labeling or something like that, we would love to have, the ability to augment our data sets with compositional objects.
Yeah. Yeah, no, that's a good point, especially with like something like object behaviors and stuff, because yeah, I feel like maybe like these kinds of things we could implement in like a 3D renderer fairly easily. But something where it's like objects that when we eventually want like objects that move and things like that, or kind of have interactive parts, that could be quite complex to implement. And yeah, no, that's a good point. That'd be cool to see if anyone in the community wants to help.
You could start with even simpler composition objects, and I think I mentioned this once or a couple of times. Like it was so confusing how compositional objects work. So at one point, I spent a lot of time thinking about two rectangles, and one rectangle represents a room, and the other rectangle represents a rug in the room or a table in the room, and just trying to understand how you could learn a model of where the table is and what angle it is in the room. So it's a two-dimensional problem with just two rectangles. It was really hard. I mean, I didn't have a solution. I couldn't figure out a solution. But my point is, we could start testing the code on some really, really simple things, just to, it's a common technique, right? You just start with something really, really simple, just to make sure the code is working and that you don't have any bugs in it, and then work up to some simpler objects that we might be able to do, and then ultimately, I wouldn't want to dive headlong into like, okay, let's start understanding a bicycle and its compositional. It's like, okay, let's say one step at a time here. So my point is, I think there's a lot of work can be done just building the code and testing out the mechanisms before you even get to something as complex as a mug. I'm not saying we don't want to get more complex objects. We do, but start out really simple.
Right.
Yeah, it also occurred to me that we are talking about moving simulators at some point. And so, if we move to a new simulation environment, we can hand design some. I don't know how this would work with the particular environment that Tristan was reporting on. I looked at it briefly, but presumably you can design your own objects to put in there. And it wouldn't be real.
Yeah, and like right. Yes, that was something that like for our summer hackathon, I stop sharing?
Just seeing you.
Yeah, that for our summer hackathon, we, in particular, Rami had kind of implemented this data set of 3D objects. This was when we were talking about doing this dinner set thing, and we might still return to this example or like this data set later, but yeah, I guess it was just a nice example of what you're talking about, Scott, that with 3D software we have some flexibility. One interesting thing, we did have a lot of problems importing this into Habitat. That turned out to be arguably much more difficult than developing the actual 3D model data set. And maybe other simulators would be easier. I don't. But yeah, it's worth thinking about the timing around the change in simulators and this stuff. I think that's yeah, another advantage that this first work with the unsupervised learning, we can just continue using YCB, given that we have a fair amount of infrastructure stuff we also have to figure out.
Gonna throw out, and I mean it's in line with the simulator thing, but and essentially game engines are simulators, but some of the game worlds are quite extensive and have essentially infinite. I'm thinking of Minecraft, like it's simple, but it's an infinite world, so it could be an interesting data set already there in a sense.
How soon could we actually jump to actually real world? I mean, you guys did that for the hackathon thing last year. I mean, the real world is easy, right? We have lots of, we don't need a simulator. I'm just wondering, at least from a vision point of view.
Yeah, I think the reason why we stayed in simulation mostly so far is that it's much easier to evaluate. Like we know the ground truth of what is currently being sensed, versus in the real world, it's very hard to objectively evaluate and run many experiments.
But I wouldn't think of like sitting out on the street corner and having a look at things go by. I was thinking more like, take real objects, you can have them on a white background or on a white table or something like that. You could have controlled environments where you say, oh yes, there's 3 objects here and this one's compositional like this and that. I'm not saying we should do this. It just seems like we spent so much time on simulators, and I'm just wondering, could we somehow shortcut that?
Yeah, that's an interesting idea for sure. I mean, one idea we had was that during the next the TVP retreat, we do like a 2-day hackathon where each of us gets a little robot kit and we do mini projects with that, just to kind of keep working with real world data. And also then everyone can take it home and everyone can do real world experiments wherever they live. But yeah, it still requires some more infrastructure to be set up.
Right.
Yeah,
it
I guess
does,
the downside is that it's harder to do repeated experiments that are comparable between everyone wherever they are.
The real world also runs in real time, which is quite slow.
well, it doesn't have to. I mean, if you're talking about static objects, you set up, I have a white table with a white background, so all I see is the objects that are there, and you start. By the way, the reason I was thinking about this, because I was thinking, we're into the discussion section here, right?
Yeah.
Okay.
Yeah.
I was thinking about this. When you're talking about this, when you're talking about unsupervised learning, I was thinking like, oh, I think the way we do that from vision and touch are quite different. They have different mechanisms involved. And I was thinking in vision, we have all these clues of what's going on. We have the parallax, and that works with one eye, right? We're constantly moving just slightly, and every time you move, you can tell what objects are in front of what other objects, what objects are behind or other objects, and that they're not the same object. So just the slightest amount of movement of your head, not the eye, but the head, gives you this huge amount of data like, oh, these are separate objects. Also we can take advantage of convergence of the eyes. That's not as important as parallax, but it's also important. And then there's also issues of like policies about, for for exploration. We know the brain uses silency detection, so it jumps to places that are interesting. These are not model based. These are just like, hey, there's more stuff going on over here. So these are kind of things that, especially the parallax one, which jumped out at me like, hey, that's something that would work in real life, and vision would be very, very important. But you can't really get that from an image, right? You got to have something that actually models depth, and you can take advantage of parallax.
Yeah, well,
And then
so last time we did the real world was we just used like the iPad camera, which sends rays out and then gets an actual depth image from
right. All right. So that may work too, but that isn't as powerful, I think, as parallax. Parallax tells you right away the two objects are not the same. If they have the slightly difference in depth, whereas I might be looking at one object that has, if I take a dumbbell and I put it at an angle to me, the depth difference, one end to the other end is not really important. What's important is that, what I'm saying, I could say, oh, that's further away, this is closer, this is separate, but no, from a parallax point of view, they're not going to be separate. Anyway, I just thought that there were some things. Then I was thinking about touch too, and I'm thinking, well, there's some things there too that it's really hard to build a touch sensor, but there too, I think having real objects in a real world suggests solutions that they make this problem much easier, really much easier.
Yeah, like I guess one of the things. So with the when we did the Monty Meets World, we did create kind of the data set where we took like those depth images of the different objects, and that included some like different kind of adversarial conditions where there was like bright light, or there was multiple objects, or there was like a hand kind of coming in and stuff like that. But one thing with that is it did limit the degree of sensory motor interaction, because then we have these like depth images that are taken from one angle, and so the Monty can kind of saccade over that depth image, but it cannot actively explore the object. And so in fact, learning still took place with a 3D scanned version of the object. And it's just a fairly complicated pipeline, because then we need to 3D scan the object, which often is imperfect. And then, as I said, yeah, at inference time, we have this one image. So it feels like I think we'd almost need to take the next step, which is to have like a robotic arm that can actually move, before we could
right.
We could do it
Or
at least to the same level that we do it in simulation now.
Right. And if we have a 3D camera, I would think we'd want to think through it maybe some more about how we could, I mean, that's a different sensor than humans have, obviously. I don't know. I just pointing out that if we're going to build systems that interact with the real world, that it might be helpful to be dealing with real world objects from the get-go, maybe not exclusively. And then we could look at some of the systems that biology uses, like parallax, which seems very, very important for vision. It has a huge step up to help with unsupervised learning.
Right.
Yeah,
Also,
the idea, instead of us having to build, or someone having to build like a complex object behavior data set in simulation. I mean, not in the next 6 months, but maybe once we actually look into object behaviors and motor policies, that we actually just go into the real world, and then we'll probably notice a lot of other things that we didn't think about when we were just doing these simulations.
I don't think it's going to take us very long to figure out how this action policies and model behaviors work. I better get to solve that pretty quickly.
Sounds good.
Yeah, remember that's my goal for our offsite, our retreat, whatever we're calling it. We'll see. All right, there's some thoughts I had there. At touch, discontinuity of locations is really important. Like with vision, you can just move your eye a little bit and you slide from one object to the other object, and you don't really know that in a 2D image. Even depth information doesn't always tell you that. But with touch, it's quite different. It's much rarer that objects are physically on each other, touching each other, that are separate objects. It can be, sure, but it's much less likely. And so, you know, when you're running around your finger around an object, it's much less likely you're going to just, you know, accidentally slide into another object. There's always going to be some point of discontinuity. Even if the two objects are touching, there'll be an edge of some sort, or an angle or something, and those are clues, right? Those are definitely clues. And then when we touch things in the real world, often we move them slightly. And if we move them slightly, and we're looking at them at the same time, then there's your parallax again. And then you know they're two separate objects. So there's a lot going on in biology and real world stuff that we don't want to kill ourselves trying to come up with alternate solutions if we have to use some of the biological solutions. Just stuff to think
Right.
about.
But I mean, just to come back to the time thing, once you put a robot in it and you're moving, now you can only run in real time.
Well, why can't the robot go slow?
Well, no, it can go slow, but from an experimental point of view, real-time experiments are going to get pretty painful pretty fast.
guess
Like if
I-
you
I
want
guess
to
I'm
run
missing
through a
why-
data set of 20 objects,
Oh, I see.
now
20
you're
objects.
going to need to put a new thing in your robot arm, wait for
I see.
15
I
seconds
see.
to go by. Like
Yeah.
that
All right,
that
well.
process becomes pretty painful quickly. Where
And-
if you were
yeah.
in a simulation environment with the physics engine, then you can pick up your objects and knock them over. And
Yeah. Well, you know, maybe the compromise is that you keep in mind constantly how you're going to do this in the real world. And don't, you know, and think about the things that are going to help in the real world, like the parallax thing. That's something we haven't really introduced at all. You think about that in the real world, and then you do your simulated world, but you make sure that the simulated world is going to work in the real world as best as you possibly can. I mean, and then you could always, you know, drop back out and test a couple of real world things. My fear in these simulated worlds is we end up solving simulated problems, and then when you go to the real world, things are quite different. And so you want to
there's
stay
a lot of
grounded, but-
research in that direction at the moment because of
Yeah.
robotics and autonomous cars.
Yeah, there's sim to real and real to sim people who are working on exactly bridging this gap between simulated world and real world. And I think when that
No.
time, well, I think we should always keep in mind of the real world. And then when the time comes where we can, or
Well, keep it-
hopefully where we understand kinematics.
Well,
a little
see,
bit
I
more,
guess
we can
I'm arguing a little
chemicals.
further than that. I mean, keep in mind is not the same as doing, right? So, you know, we might think about doing it so it does work in the real world and test it in the real world, but then don't run all your tests. As Michael was saying, you know, that can be very slow. But I think the real danger is saying, oh yeah, we'll get to the real world eventually. Let's stick to the simulated world. I don't know, it just
Yeah, I think a fun way to encourage this could be to have like every 6 months we do like a real world hackathon where we implement, like where we actually work with real world data and try to solve different problems using our current algorithm. But then on a day-to-day basis, when we evaluate our experiments, we still run them in simulation, run our benchmarks in simulation.
Well, there could be a hybrid of that, was like you run them in simulation, but then you always have at least one sort of test, like you did in the hackathon, you know, Monty Meets World. We do one real world test just to make sure you're not losing sense of reality, you know.
Like what I'm hearing that ought to be possible, right, is we currently have unit tests, integration tests, end-to-end tests. This would be like real world tests, right? So it would be probably the slowest one that runs the least often, but at least we would be beginning of the feedback loop that's
Right.
regular,
You
right?
think of the real world test as like a unit test for the real world. How about that? Right. Because we don't have to do anything super sophisticated.
Yeah.
We just have to make sure it kind of works.
Somebody runs it once a month or once a week or something, but it's the start of that feedback loop, and then we tighten and tighten and tighten it as
Yeah.
we go on.
Yeah,
I wanna-
HP did something like that
Yeah.
for their printer tests. They automated the real world part of it as well. So like in part of their test suite, HP also tested like building one print cartridge or something in an automated function.
Maybe next year I can once a day run the real world test of washing my dishes with Monty.
I
Just
wanted
to
to
make
ask
sure it still works.
I wanted to ask because Jeff keeps something in parallax and like that's I just want to do a check of my understanding, right? But parallax is something we can test with existing things by adding an agent that moves the distance sensor's location stochastically, and as long as we integrate that information to the agent's location, that's will generate parallax, right? It doesn't control the head movement, but just imagine it's an eye that's stuck on the head, and the learning module.
Right, it's a
The dis
model-free, it's a model-free policy, right?
Right.
So yeah, you could just move your head a little bit left and right.
and
So
so
it doesn't have to be stochastic, it could just be
oh, okay,
continuous.
yeah. So
I mean,
that seems like that's a actually very nearby experiment that we could add as we're
but would you do
figuring
that
out.
on real objects or you do that in the simulator?
No, it's in a simulator. It's an agent sitting in it. It's just moving the agent location versus turning the a distant agent, right?
Yeah,
Yeah. It's
Yeah.
the first person shooter moving.
so that would be good. So that's exactly, I think, like, you think about parallax, because that's something that we know biology does, and it's really powerful. But so it may be something we want to include, even if we're doing it on simulated objects in this. So I think Tristan, that was exactly what I was sort of arguing for, somehow keeping the real world in our thinking here.
Yeah, yeah, and it definitely appeals the idea that we're not too reliant on specifically depth-based cameras or like cameras with depth, because that is quite
Right.
a strong
Right,
assumption.
it doesn't. It's not the depth isn't as an important indicator than as parallax. Of course, we're not really aware that the parallax is happening. We just sense that objects are different or different depths, and we just know it. But how do we know it? And it works with one eye, so it's like it's okay. We're not relying on two eyes. It's parallax. That's the answer. I mean, there's a small amount of lens when you focus at different depths. The lens changes a little bit to get it in focus, but that's not. I don't think that's nearly as important signal.
Yeah,
Yeah.
I mean, sometimes there's some of these things that, like in general, it feels like a lot of the subcortical stuff is where, if we are going to ever use deep learning in Monty, like that's where it could be useful. And like, for example, deep learning is quite good at like doing just basic figure ground segmentation, where it's just like gives a core sense of like, oh, what are the objects near me? What is their approximate depth, or whatever, and what are the ones far
Is
away?
it doing that
It uses,
on images, or is it doing that on real world?
there's lots of different systems, but some of them are specifically video based.
I guess I'm saying is
Yeah,
even video is images. I mean, the thing I think we're going to create systems that work in the real world. I see it seems like crazy just to make a system that work with two-dimensional representations of the world, because we're going to be moving through the world. And our agents will be moving. They'll be moving not just their eyes a bit. They'll be moving their bodies, and they'll be rotating things. And so, I always felt that the reliance
as in, so
on
your point is, you'd want it. I mean, it would still be a video, wouldn't, but as in your point is, you'd want to make sure that like the agent or the system, whatever, is moving, and it's that kinds of video that it's.
Well, video. The problem with video, that's what I see on my screen. I see a video, right? It's
Yeah.
I've made this comment multiple times in talks I've given in the past, where like computer vision isn't vision. It's like it's not vision at all. Vision is an agent moving through the world, moving its eyes, moving objects, and that's the problem we have to solve. So we have to be really careful not to try to solve the image on the screen. I don't even know it's possible to learn the world through a 2D presentation like that. It's certainly we're able to infer after we've learned the world, right? But I think it's likely that you really can't. We couldn't learn the world by looking at 2D representations of static images or moving images. We can do a pretty good job of inferring it later, but I don't think you can learn that way. Certainly, we have much harder. But I think I liked I can't already forget who said that. It was Tristan's idea, just or Michael's, whoever saying, oh, you just add a little bit of movement to the eyes in our simulators. That's pretty cool. I like that idea.
Yeah, that was Tristan's idea. And yeah,
Yeah.
we could, sounds like a pretty quick thing to add and test. Could be interesting.
Right.
Yeah, if
And
we
the
have a
touch
couple.
sensor, yeah,
Go ahead.
go ahead. No, yeah.
I was just gonna say, if we have a couple more minutes, I could go over the last slide, which covers a bit more of the rightmost column of like the community aspect and make it easy to use. But I just want to make sure we first discuss everything related to the research roadmap. So if you have more comments on that.
Well, I have an idea that I'm writing up for object behaviors, but I don't have to do that now. I can just write that up and post it, and we can talk about it another time.